talks, and the tea break will come back to the assembly about 5 minutes before 11.
Yeah, tea is in the dining hall right next to this lobby. So somebody.
Technical fashion later on, but since I'll be looking at issues concerning granger causality, let me give you an intuitive sort of picture of what granger causality is about before I proceed. So granger causality essentially tries to quantify the causal relation between two processes. So let me take a very sort of non-biology example. So suppose you have you are measuring the global carbon dioxide concentration every year, okay, the global mean carbon dioxide concentration, and you are also measuring the global mean temperature every year. Then you are very interested, as far as say climate change studies are concerned, whether there is a causal effect from the global carbon dioxide concentration to the global mean temperature. That is, whether the increase in global carbon dioxide concentration is causing an increase in the global mean temperature. So those are the sort of issues we are interested in when we use granger causality. So granger causality essentially quantifies this causal effect. So given these two time series data, that is, you have data measured every year or every second or whatever, and you have two such time series data, then you want to see whether one process has a causal effect on the other. That is, whether the past of one process helps you predict the future behavior of the other process. And essentially granger causality quantifies that, and that's what we'll be looking at. So granger causality has been very effective in analyzing neuronal activity directly. So suppose you have LFP, local field potential recordings, or EEG data, things like that. There, it has been used quite effectively in looking at causal relations between different regions. But there are issues, as we shall see, in using granger causality for FMRI data. And as all of you know, FMRI recordings have become very ubiquitous, and several groups have now started applying granger causality analysis to FMRI data. And this is not just of mathematical interest. Let me give you one application which has been gaining a lot of traction recently, a clinical application. So it turns out that there exists what are called these resting state networks. So you have, the person lies in the FMRI machine, and let's his or her mind wander, essentially do not do anything in particular, and then you record the FMRI data from such a person, and it turns out that almost all adult human beings have essentially the same connectivity pattern in the resting state. So you have a series of brain regions which are connected by certain connectivity pattern, and this is the resting state connectivity pattern. And more interestingly, what people have observed is that in cases of neurodegenerative diseases like Alzheimer's and Parkinson's, there are changes in this connectivity pattern. And these changes happen before the onset of clinical symptoms. So essentially what you can do therefore by looking at these, measuring these connectivity patterns, the resting state network connectivity patterns, and looking at changes in these connectivity patterns, that you can get functional biomarkers for the onset of diseases such as Alzheimer's. And in fact, several companies are now trying to exploit this. They've gone into phase 1 trials, phase 2 trials, and so on, of trying to predict the onset of Alzheimer's by using such devices. So essentially, therefore, you can see that getting reliable connectivity patterns between different regions is not only of interest as a mathematical problem, but also has potential applications. So since fMRI data is becoming, as I said, more and more ubiquitous, so you are also interested to know whether granger causality can be applied to this problem. There are issues involved in that. So the reason why it's more complicated in applying granger causality to fMRI data is because the fMRI measures the blood oxygen level independent signal, and it's not directly measuring the electrical activity of the neurons. So you have this bold signal, and which is an indirect measure of the neural activity. So mathematically, what you can think of is that the bold signal, the fMRI signal that you observe, which I call it as y of t, is a convolution of the neural LFT signal x of t with this what is called the hemodynamic response function. So you have this neural signal which is being convolved with this hemodynamic response function, and you get this x tilde, which is what you observe. Okay. So this is what you are actually measuring in fMRI, and so if you look at the details of this bold signal, the bold signal increases about 2 seconds after the neural activity begins, and then it reaches a peak at about 5 to 8 seconds after the neural activity begins, and it will plateau if the neural activity continues, or it starts to die down and returns to a baseline 8 to 11 seconds later. And there's also an undershoot, there's a transient phenomenon of undershoot. And mathematically, one model of this hemodynamic response function is given by this, which is a combination of two gamma functions, but you not worry about the details, where L is the sampling interval of the neuronal signal, tau is the onset delay, how long it takes for the bold response to begin, and tau prime is the corresponding time for the undershoot, and C is the ratio of the response to the undershoot. So these are various parameters which come into the HRF, and this is how it typically looks like. So you have this peak which happens 2 to 4 seconds later, then there is this undershoot, and the main problem, one of the issues which complicates use of granger causality for fMRI data is that the different regions can have different hemodynamic response functions. That is, these hemodynamic response functions can peak at different times in different regions of the brain. Then you can imagine that this can cause problems in applying granger causality, because for granger causality application or any causal analysis or any such application, the time flow is very important. What occurs first, what occurs next, and so on. Now, if suppose you have two processes, and process A at the neuronal level is causing process B, but the hemodynamic response function for process A peaks much later than the hemodynamic response for process B, then you have a conform, because that can act against the time flow which is happening at the neuronal level. So you have such issues in applying granger causality to fMRI data. So there are two ways of looking at it. You can treat the bold response, the fMRI data, as a signal in its own right. You don't worry about what is happening at the neuronal level. You just say that, okay, I'm interested in the bold response and how the bold response gives connectivity patterns. And that is also a valid thing. For example, I was valid approach because I was talking about, for example, say whether you can distinguish between onset of the Alzheimer's condition and normal and so on. There you are only looking at differences between two different conditions. So you are not, even though biologically you may be worried about what is happening at the neuronal level, but as far as detecting something is concerned, all you are looking for are differences between two conditions. So you might as well do it at the bold signal level, because if you can find a consistent difference between non-Alzheimer's and Alzheimer's at the bold level, even though there may be complications in mapping it to the neuronal level, you don't bother. As long as you get a consistent interpretation at the bold level, so you could do it there. So that is one approach, and that is also taken, of course. But we here, as far as this talk is concerned, we are interested in seeing whether the connectivity you observe between the causal connection you observe between two regions at the bold signal level, at the fMRI signal level, is consistent with the connectivity pattern which is actually there at the neuronal level. So whether there is a consistent mapping between the two. So that's what we are interested in. And as I said, the variations in when the hemodynamic response function peaks in different regions can lead to problems in doing this mapping consistently between the neuronal level and the board level. And also there's one other issue, which is in fact it turns out is a more serious issue, that the neuronal level, things are happening at a very fast scale, but the fMRI, given the limitations of technology, you are measuring the fMRI signals at a very low sampling rate. So typically, it is 1 second, you are sampling fMRI at 1 second, 1 per second, or every 2 seconds, or these days with more modern machines every half a second and so on. So there is a lot of downsampling going on from what is happening at the neuronal level and what you are measuring using fMRI. Okay, so so that is, as you shall see, is again an issue. So now let me actually come to quantify what actually this granger causality is, and then you'll see how these two issues affect granger causality, that is this hemodynamic response function having variations across different regions of the brain, and the downsampling which is done when you go to fMRI signal. So as I mentioned already, granger causality essentially quantifies the causal effect one process has the other, and this was introduced by Granger in economics. So this first was done in economics, and this concept of causality, and I'll talk about autoregressive process in a minute. So these two concepts have had a huge impact in the field of economics. In fact, 2 Nobel Prizes have gone to this work. One to Granger, who got a Nobel Prize, and last year Sims got a Nobel Prize for causality and multivariate process in these things. So you have this concept of causality and autoregressive processes has had a huge impact in economics. And what has happened recently is that the use of these concepts has percolated to other disciplines, including neuroscience. So as I said, there's a lot of work which has been done, including by us, on applying granger causality and extending granger causality to analyzing neuronal level signals. So you have this basic setting is this. So you have 2 recordings of data. So in our context, you could think of it as recordings from 2 different regions of the brain. So it could be LFT recordings from 2 different electrodes, or in the fMRI case, it could be recordings you have from say 2 regions of interest. So what the basic mathematics, underlying mathematics is that, again, don't worry if you are not familiar with these terms. So essentially you will treat these 2 time series data as realizations of some underlying stochastic process. So that is the underlying mathematics which goes into this concept. And what you then do is you introduce what is called an autoregressive representation of a process. That is, you say that suppose I have 2 processes, x1 and x2. So first what you do is you try to predict the current value of x1 using only the past values of x1 alone. Okay? So since this is a stochastic, so this is called an autoregression. You are all familiar with linear regression, where you try to regress one variable against another variable. Okay, so you may be regressing in economics, for example, money supply against inflation rate or something like that. Whereas here you are regressing the process against itself. That's why it's called an autoregressive process. So essentially you are regressing x1 at time t against x1 at the previous times. So the basic idea is that you are trying to predict the current value of x1 using only the past values of x1 with an appropriate weightage. So this is what is called an autoregressive process. Now, since these are all random processes, so you have an error which is called epsilon 1. I will call it as epsilon 1. Now, next what you do is that you then try to predict the current value of x1, not only using the past value of x1, but you also use the past value of x2 to predict the current value of x1. So now we are putting in more information. You are using not only the past of x1, but you are also using the past of x2 to predict the current value of x1. Then you get some other error, which I call it as epsilon 1 given 2. Now, if this error is smaller than this error, then you say that x2 has a causal effect on x1. So essentially, granger causality, like many great areas, is essentially very simple as far as the concept is concerned. That essentially you are saying that if another process helps in predicting, so if the process x2, the past of x2 helps me in predicting better the current value of x1, I will say that x2 has a causal effect on x1. Okay, so that is quantified by looking at the size of these errors. So if x2 helps in predicting x1, obviously the size of this error is going to be smaller than the size of this error, because the prediction is better. Okay, so that is what essentially granger causality does. So you quantify it in this manner. So you say that if the variance of the second term or the second error term is smaller than the variance of the first error term, then you say that x2 has a causal influence on x1. Okay, and this is quantified by taking the ratio of these two variances and taking the logarithm. So that quantifies granger causality, and you can see that by incorporating x2 process, the past of x2, if you have no improvement in the prediction, then this error at the denominator is going to be the same as the error in the numerator. So the ratio is going to become 1 and the logarithm is 0, so you have 0 causality from 2 to 1. Again, I'm just giving all this, but you should do all this in a statistical sense. So you have to look at statistical significance and all that. So I'm not getting into those, I'm just giving you the underlying concept. So you have the quantification of causal relation from 2 to 1 using granger causality. And you can do the similar procedure for looking at causality from 1 to 2. That is, you look at trying to predict the current value of x2 using the past of x2 alone. Then you get some error epsilon 2. Then you try to predict the current value of x2 not only using the past of x2, but you also try to use the past of x1. And you get another error. If this error is smaller than this error, then obviously using the past of x1 has helped you predict x2 better. Therefore, you say that x1 has a causal influence on x2. Okay. So this is again quantified by this ratio. So you can have causal influences from 1 to 2 and 2 to 1. So you can have causal influences going both ways. And the advantage of this over traditional correlation analysis which is used is that the causal analysis takes into account the internal structure, the correlation structure of the process. So you are not only trying to see the effect of x2 on x1, but you are also incorporating the internal correlation structure of x2. Okay, because you are first modeling it using x2 and then putting in x1. Okay. So that is the advantage granger causality has over the traditional correlation analysis, and that is why it has become very popular. Okay, so therefore we have this quantification of granger causality between two processes. Next, we'll be interested in looking at granger causality in the frequency domain. So many natural processes, of course, are very interesting to look from a frequency component viewpoint. For example, even in signals recorded from the brain, you may be looking at alpha rhythms, beta rhythms, theta rhythms, whatever. So you may be interested in seeing whether there is a causal relation from say region A to region B at a particular frequency. Okay. So you may be interested, for example, in seeing whether there is a causal relation from A to B in the beta at say 20 Hz. So whether there is a causal relation. So that is something which is again important, and it will also be useful in looking at the effect of convolution and downsampling on granger causality. So let me not go through this math. So essentially what you do is you have to do a Fourier transform of the signals and look at the covariance matrices of the noise terms. So you have this covariance matrix of this noise term, and then do some manipulation of these. So essentially what you will have is that you will have such a representation where this is the spectral representation of the autoregressive process I talked about, and this is the spectral representation of the error term, and this is the spectral representation, frequency representation of the process itself. So you have this something like this, which is there. AF acting on XF is equal to EF, and then it turns out for autoregressive processes that we're interested in, you can invert this and you get X in terms of the error through what are called these transfer function matrices. So the concept of transfer matrices comes from the electrical engineering literature. So once you have this transfer functions, you can build what's called the spectral density matrix, S, okay, in terms of this transfer functions and the covariance matrix of the noise. So you have this, where essentially the diagonal terms in the spectral matrix correspond to your usual power spectrum of the process. So you might have used the power spectrum of a process, and the diagonal terms would correspond to the one term would correspond to the spectrum of the process 1, and two term would correspond to the spectrum of the process 2. Anyway, so you can here the basic concept when you translate it to the frequency domain becomes this. You look at the power of process 1 at a certain frequency, and then you see how much of that power comes from process 1 itself and how much of it comes from process 2 at that frequency. Okay, so this is the translation of that error which I talked about in the time domain to the frequency domain. So again you have to do some further analysis. Let me not get into that, but essentially what you have ultimately is that you have this expression, quantification of granger causality at a frequency f from 2 to 1. Okay, so this is the auto spectrum, bar spectrum of process 1, and this denominator is a contribution to the auto power from process 1 itself, because I am subtracting out the contribution from the second process. So if the second process, so if this term is 0, then the second process would not contribute anything to the power of the first process. So the numerator and denominator would be equal, and again granger causality would become 0. So this is the basic concept in the frequency domain, that you see, you look at the power of process 1 and see how much of the power is contributed by the process 1 itself and how much of it is contributed by process 2. And if the process 2 is contributing some non-trivial amount of power to the process 1, you will have a granger causal relation from 2 to 1. And you can again do 1 to 2 similarly. And by integrating this granger causality of all frequencies, you can get back the granger causality in the time domain. So now let's go to the effect of convolution and downsampling on granger causality. So this is a Fourier transform of the neuronal signal. X of f denotes the Fourier transform of the neuronal signal, and you would know that convolution in the time domain by this HRF function corresponds to a multiplication of the corresponding Fourier transforms in the frequency domain. So you will have, I'm using for right now the same HRF function for both x1 and x2. So x is a vector here, it has x1 and x2 components corresponding to the two processes. So you have that x tilde is a Fourier transform of the board signal. So you have the convolution of the HRF with the neuronal signal, and that gives you x tilde, which is the Fourier transform of the board or FMRI signal. So you can substitute it in this, and you can follow the standard procedure which I skipped over and obtain granger causality for the board signal, and what you get is in fact an identical expression as what you had earlier. So what this mathematical analysis tells you is that if you have the same HRF convolution for both the regions, or if there are not significant differences between the HRF convolution for both the regions, there is no effect on granger causality. That is, the granger causality at the neuronal level gets exactly mapped to the causal effect between the two regions at the bold level, at the FMRI level. There are some complications if you have different convolutions in different regions, and we will handle that numerically later on. There are some issues which I'll talk about later. So the simple case convolution has no dramatic effect on the granger causality. Now let's look at downsampling by a factor of 2. So I'm modeling again the FMRI, the signal by the neuronal signal by this autoregressive process. So I'm taking the simple example of an autoregressive process of order 1. That is, here I assume that x at time t can be predicted by using only one term, x at time t minus 1, just the previous time step. Okay, and then there is an error. Now I iterate this, so I write that by using the same expression again for t minus 1, I can write x of t minus 1 as a times x of t minus 2 plus e of t minus 1, and I do this and I finally get this expression. And if I do this mathematics, it turns out that this e prime, which is this term, a e t minus 1 plus e of t, that is again a Gaussian process. I can look at properties of that and I see it's uncorrelated, so it's a white noise process and so on. So let me not do all the mathematics, and what you get is that this E prime process has this sort of covariance matrix. So ultimately, I can what I therefore do is what you do when you downsample by a factor of 2, you are only sampling at every alternate time point. So if I am measuring the signal every second, when I downsample, I will only look at time t equal to 0, 2, 4 and so on. So that essentially corresponding to skipping the every alternate time point, and if I do the math correctly, what I get is that the downsampling corresponds to yet another autoregressive process, except that this A prime, the coefficient matrix here, is replaced by A squared as far as the original process is concerned, and your covariance matrix of the noise is replaced by this complicated expression, and you have this downsampling. That is, you are measuring only every second term. So this is what you get. So you essentially, if you then translate it to granger causal quantification, then you have to replace A by A prime, where A prime is given by A squared, sigma by sigma prime, and Fs is sampling frequency by Fs by 2. So that is the change you get by downsampling. So this is what you have. Now, if A is an upper triangular matrix, okay, so that is upper triangular is where you have no entries, the bottom triangle of the matrix, then it turns out A to the power d, if you keep on taking powers of A, that still remains an upper triangular matrix. So, so if you have no granger causality from region J to region I, for J equal to greater than I for the neuronal level, there will be no corresponding granger causality at the bold level. That is, no spurious granger causality effects are introduced at the FMRI level by this downsampling. Okay, but then it's more complicated. For example, if you have such an A, what this tells you is that 1 has a causal, 2 has a causal influence on 1 with the strength B, and this 1 has a causal influence on 2 with the strength C. If you have such a matrix A connecting 1 and 2, then you see that if you take the square of this matrix, it's diagonal. So the off-diagonal terms are gone when you have such a matrix, and that implies that granger causality is also gone. Okay, because the granger causality comes from these off-diagonal terms, which measures the influence between the two processes. So essentially then this tells you if you have such a connection matrix, the connectivity which was present at the neuronal level is completely lost when you go to the FMRI level. So you have a spurious result that what was there at the neuronal level you are not at all capturing at the FMRI level because of this. downsampling. Or you can take such a more complicated with 3 processes interacting, 3 regions in the brain interacting with one another, and suppose you have such a structure, then if you take the square, you see you get a non-zero element here. This was 0 here, that is there was no granger causality between process C and A, whereas you get a non-zero element here which tells you that there is granger causality between the process 3 and 1, or process 3 and 1. So you have introduced this curious granger causality. What was not present at the neuronal level has been introduced at the FMRI level. So you have, and even though I'm talking in terms of granger causality, all these considerations will apply to correlation analysis and all these other analysis that we do. So this is a serious issue. That is, you see that when you're looking at these connectivity patterns, either using correlation or granger or whatever technique you have, what is present at the neuronal level may not be present at the fMRI level because of this downsampling. What is not present may come spuriously at the fMRI level. So one has to be very careful in doing fMRI connectivity analysis because of all these curious effects which can come from the severe downsampling that you do. But again, as I said, this is only valid, this whole analysis is, all these concerns are valid only if you are trying to map the board level signal to the neuronal level signal. If you are only interested in analyzing the board level signal as a signal in its own right, and if you are trying to distinguish between different conditions, then everything is okay. So you are only at the board level. So, okay, but it turns out things are not so bad, even if you are trying to do the mapping between granger causality at the neuronal level and the board level, because often what we are interested in is the changes in the connectivity pattern, the changes in causal relation between 2 experimental conditions. So you are trying to distinguish whether there are changes which are happening because of 2 experimental conditions. And there the situation, as we shall see, is much better, because suppose you have some underlying system parameter which is varying. Here I've taken the case for simplicity of monotonic variation. Suppose you have some, you are looking at 2 underlying conditions, 2 experimental conditions, and some underlying parameters varying monotonically from condition A to condition B. Then what we'll see is that despite all these problems in applying, say, causality or correlation or whatever connectivity analysis, if there is a change from condition A to B, that change can be preserved, even though the magnitude of the change can differ, it can change and so on, but at least the right sign of the change is preserved when you are going from one condition to the other. So that is what we shall see. So essentially again looking at neuronal signal which is being modeled by this auto-regressive process. So you are predicting x at time t using x at time t minus 1 with an error, and let me again, this is all, you can do a more general analysis and just giving it here for simplicity. And by construction you see that causality exists only from 2 to 1, only this off diagonal term is non-zero, and this is the expression that you get. And if you do the downsampling, as I said, you have to replace a by a prime, which is a squared, so this is what you get. Again, we go through the math, and you get an analytical expression in this case for granger causality after downsampling by a factor of 2. And rather than exhibiting the full expression, I've just shown you a graph here. So the original signal is this. So as this parameter b, so the b essentially tells you, if I go back to this expression, see b appears here. So as b increases, the granger causality increases. Okay. So and if b is 0, granger causality goes to 0. So that is the off diagonal term here. So you see that as b increases, indeed in the original signal without downsampling, of course, the granger causality increases. But even after downsampling, even though the change is different, but still it increases. Okay. So that's what I mean by saying that the monotonicity is preserved by this transformation from the neuronal signal to the FMRI signal. So if you have two different conditions, one corresponding say to mathematically to a B value of 0.2 and another corresponding to a B value of 0.4, then if you are looking at a neuronal level, you would see such a big change, say from 0.1 to 0.2 to you can see that in fact the original granger causality and the granger causality of downsampling vary monotonically with one another and so on. And then you can do something more complicated where you can include both downsampling and the convolution with HRF. And what you get is, in fact, it becomes better. That is, the change from the original to the downsampled and convolved signal, the FMRI signal, is not so much as with only purely downsampling. That is because when you are convolving with the slow HRF signal, you are essentially stretching out, you are spreading the information across a much longer time region. So even if you downsample, you are still able to detect connectivity patterns between two different regions. So in fact, downsampling makes it better, and again you see the monotonicity. And one can do a much more, this was more at the analytical level, looking at simple models, but one can do a much more careful numerical simulation, making things much more realistic. For example, where you have the neuronal signals which are convolved with the local HRF function, then the sampling interval at the neuronal level is taken to be 15 milliseconds, and it is downsampled to a time resolution of 2 seconds at the FMRI level. So this is essentially, the blue is the original neuronal signal, and then you have the green as a final FMRI after adding noise and all that, measurement noise and so on. So now if you look at the monotonicity between the granger causality at the neuronal level and at the FMRI level, you still get the monotonicity between the two. And this is at the bidirectional case, and you can look at various measures of how these things do. So since I'm running out of time, I will not get into the details. So I'll just say that things, are get worse as the sampling, as you can expect, as the sampling interval becomes larger or the sampling frequency becomes larger and larger. So if you are sampling only every 1 second, things are better. If you are sampling every 3 seconds, things become worse. But the good news is, as technology is advancing, the sampling rates are in fact going down. We are already down to 0.5 seconds. People are looking at doing FMRI analysis for small regions where they do much higher sampling rates now. So we are in fact moving towards this direction. So things would in fact only get better as the technology advances. So, but if you are using older FMRI machines which have very low sampling rates, then it can be an issue. That is, you can see that the prediction rate, the correct predictions drop as you have older, larger and larger sampling intervals. And in terms of, you can do some things to alleviate this. You can correct for problems which I mentioned. One is that one can do what's called a breath holding task, and by which you can estimate the HRF delays in all regions of the brain, and then use those HRF delays to correct for differences in onset of HRF. So if you do that, this is what we have done here. So if you do not correct, the true prediction rate just drops as you have differences in the HRF latency, the time at which the HRF peaks. But if you correct for it, then you get a pretty flat thing where the prediction remains pretty good. So there is a nice mapping from bold signal, from the neuronal level signal to connectivity at the bold FMRI level. So you can do the same thing for different conditions. So let me conclude saying that so granger causality is a very well established technique for analysis of connectivity patterns at the neuronal level. But there are issues in applying granger causality or any other connectivity analysis like cross correlation or correlation analysis at the bold FMRI level, because of two issues. One is convolution with the HRF function, and the other is downsampling that you do in going from the neuronal level signal to the FMRI signal. So especially downsampling is quite bad, and that can destroy granger causality or introduce spurious causality and so on. But what we see is that as technology is improving, as sampling rates are becoming better, in fact all these things would get better. And the other thing is, if you are only interested in looking at changes between two experimental conditions, again these things work fine. So this is the basic message. Okay, thank you.
Can the granger causality estimate from the time series be conditioned on things like diffusion tensor image or something like that? Is that a viable thing?
Yeah, you can, because these are all probabilistic concepts. So you can always condition on different things and use, but I don't know whether people have done that. But yeah, you can put it, in a Bayesian framework as priors and then do these. Yeah, it should be possible. I'm not aware of, work but that's definitely possible. Yeah.
Just like how you have microstrates in samples, can you have anything like that so that you don't lose information?
Yeah, well, essentially you were saying there's nothing like a Nyquist rate here, because what you see is a gradual increase as the sampling rate becomes better and better. So as a gradual increase in the quality of the prediction as the sampling rate increases. Okay. So there's no such thing, there's no theoretical thing like a Nyquist frequency that below which everything is fine, above which things are problematic.
Yes.
So I'm interested in, so if you were to just use the low frequencies in the LFP arms, and basically do a low pass filter below like 2 seconds or 0.5 hertz, would that then be, in some sense that's downsampled, would that then relate more closely to the granger causality of the...
Yeah, essentially that's what in some sense you are doing. With the HR, the board signal essentially does such a thing, a low pass filtering of the neuronal signal. So you would have these issues even if you do downsampling, a severe low pass filtering of the LFP signal.
So using FMRI for an analysis of the resting state is of course interesting and done, but it has a very poor time resolution, as you said. And do you plan, or it would seem much more reasonable to use magnetic encephalography or EEG for studying the resting state?
Okay, as I said, the resting state, many people are often using the connectivity patterns as a functional biomarker for diseases. Well, they're doing other things. But if you're only interested in this concept, in this application, clinical application, potential clinical application, then it would really not matter as long as you can get a consistent interpretation between a disease state and a non-disease state, whatever signal you are using. Okay. So as long as you get a consistent difference, it should not matter. But if you are interested in looking at the mapping between what's actually going on at the neuronal level, then what this says is using much higher time resolution would definitely help.
So two questions. First is related to sampling. You talked about temporal sampling. What about spatial sampling? Voxel sizes are changing and granger causality matrix. You add one more channel to it and all your estimates fall apart.
No. You just do no. They don't fall apart. When you increase the sampling, in fact, we have done work on what's called non-parametric estimation of granger causality, where we estimate granger causality for this entire, say, matrix of voxels, of all the voxels you have. Then you can pick submatrices out of it and do it. So then you have a consistent estimation of any subpart of it on the whole and everything. So that part, the spatial thing is not an issue. That will just tell you whether you are looking at causal relations between two large regions of interest or two small regions of interest. So that's where that would make a
Is there some correction one could make? Like if I know within a small area that these voxels are highly correlated, so I can lump them as one node and then.
Yes. So one can do that. In fact, we have developed again some measures called block coherence where we can treat all the things voxels in one region as one element, and then another voxels in another region of interest as another element, and look at correlation between the two. Yeah, one can do that. Yes.
Okay, second one is a more general remark. I mean, in recurrent systems, how good is the definition of causality in general? I mean, granger causality, yes, it's a measure, but the concept of causality for recurrent networks.
By recurrent systems, you are saying that, I mean, my general understanding would be that things repeat after
Well,
the
there are
process,
all kinds of loops and.
Oh yeah, those things,
right.
oh no, loops etc. wouldn't matter. I mean, because I was thinking of recurrent dynamical systems where things repeat
That
after.
also is true,
Yeah.
because there are loops in the network and then dynamics, of course.
Yeah. If you are measuring everything, granger causality can tease out all these loops and everything. Because granger causality, the nice thing is it goes both ways, so it can pick out loops, everything can be done. The problem would be when, for example, you are measuring two processes, there's a third process affecting it, and you are not measuring the third process. Okay. So then, of course, with any, and the best you can do is with the available data. So if you have not measured the third process, then you can get into problems of looking at causality between the two, and you have no information about the third, which is also having an effect on.
Last question.
So why is downsampling required?
Oh no, that is a technological limitation. That is, FMRI machines now measure signals only every 1 second or 0.5 seconds. But as I said, technology is improving, so you are getting faster and faster machines. But yeah, so there is a severe downsampling because of technological limitation.
Any other questions? All right, so we should thank